In this lecture video, we're going to look at frictional forces, but instead of using the normal force in our friction equation, we're going to use contact forces. So our first example, let's say that we've got a nice little crack in a rock. That's what that is right there. And rock climbers use this thing called a cam. And a cam is this little spring-loaded device. And you pull the trigger, you stick it in the crack, and then you release the trigger. And the spring-loaded device pushes against the sides of the crack. And it allows you to essentially hang off of that little cam device. And so the question here is, what is the minimum coefficient of static friction to hang some kind of big mass like a person? All right. So we're going to ignore the mass of the cam because it's so small compared to the mass of the person. So the free body diagram then for this whole system is we have a contact force between the rock wall and the little cam device. And the contact force goes in that way, F sub c, and then it also goes in that way on the cam device, F sub c. Now these contact forces between the wall are equal and opposite, so they cause a frictional force, and this is static friction, that goes up. So we have a force of static friction between the wall and the cam device on the right-hand side, and we have a force of static friction between the rock and the cam device on the left-hand side. Two contact forces, two frictional forces. And then we have the weight from our rock climber going all the way down, so mg. All right? So we know here that the sum of the forces is equal to 0, or the rock climber hopes that it is, because they don't want to accelerate downward. They want to hang there. All right? So forces acting, let's see here. We care about the y forces more than anything else because the rock climber doesn't want to fall vertically. So vertically, let's say up is positive. We have Fs plus another Fs is not equal to minus that mg is equal to 0. So we have 2Fs then is equal to mg. Using our friction equation, we can rewrite friction as this time we're going to use the coefficient times these contact forces here. And the contact forces are really what we care about. And then this is going to equal mg. So then the minimum coefficient of static friction is going to have to be mu sub s is equal to mg over 2 times that contact force. So the bigger the contact force, the more the coefficient, the bigger the contact force, the more the force of friction holding this guy up. The bigger the coefficient, the bigger the friction force holding this person up. So here we see that it's the contact forces between the objects that's really affecting the force of friction rather than the normal force. So in this case, we're going to use this equation for the friction rather than coefficient times normal force. All right? Another situation where we might see this. Sorry, actually, I just want to go back really quickly. And again, talking about this contact force here, I told you it's a spring-loaded device. So the more tight the spring, the bigger those contact forces pushing into the side of the wall. So we have a really tight spring on that cam device, and it gives a big contact force pushing in against the wall, which gives us a big frictional force. Also, it's metal on rock, some rough rock, so our coefficient of static friction is pretty large. All right, but again, you can see that the bigger the contact force, the bigger the force of static friction. Also, the bigger the coefficient, the bigger the force of static friction. Okay, going to another example that we're going to see. Let's say that we've got a textbook of mass m sub t, and then we have a block on top of that textbook, mass m sub b. And now let's say that I'm going to apply a force to the textbook, F, right here. And there is friction between the textbook and the block. To make things a little bit easier for this example, there is no friction between the textbook and the table on which I'm pushing it. All right, so some questions that we can ask. Let's give some givens here. Let's say that the coefficient of static friction between the block and the textbook is given. So the question that we can ask here is, what is the maximum force F so that the block doesn't slide. So if we push with too much F, then the force of friction that's occurring here between the block and the textbook is not going to be large enough to force the block forward at that acceleration. So we want to know what that maximum F is so that the block doesn't slide. The key here is the free body diagram for the two objects. Let's start with the block. The free body diagram for the block, we have, yes, the weight going down, so that's mBg, and we have the contact force between the block and the book going up. Now here's the tricky part. The block wants to slide backwards in reference to the textbook, and it's friction that keeps the block from sliding backwards. So since the block wants to slide backwards, friction is going to oppose that desire, and it's going to apply a force forward. So this is the force of static friction between the block and the textbook, and it is going to the right. That is the only horizontal force acting on the block, nothing else. That friction force is the reason the block accelerates to the right. Okay, now a free body diagram for the textbook. We have mass of the textbook times g going down. We also have the contact force. This contact force, which the textbook pushed up on the block with, Newton's third law pair, is going to go down this way, F sub c. And we are going to have a normal force counteracting both of those, weight and contact force. And here is a huge key as well. This static friction force is not just acting on the block. That static friction force is also acting on the textbook. This is a Newton's third law action-reaction pair. Okay? The force of friction acts to the right on the block, which means that it acts back to the left on the textbook. Those two forces are equal and opposite. They are a Newton's third law pair. All right? Just like the two contact forces. And the frictional force is going to depend on that contact force, not on the normal force between the table and the book. The normal force between the table and the book doesn't matter because there is no friction between the table and the book. Okay? So when we do Newton's second law for the block, the sum of the forces acting on the block is equal to the mass of the block times the block's acceleration. The sum of the forces acting on the textbook is equal to the mass of the textbook times his acceleration. If the block does not slide on the textbook, then those two accelerations are the same. If the block does slide on the textbook, two things are different. This is not static friction anymore, this is kinetic friction, and the two accelerations are not going to be the same for the textbook and the block. And we will see problems like that. So fleshing these out a little bit more, on the block we have only one horizontal force acting, and that's the force of static friction. That's going to equal the mass of the block times the acceleration. Okay, here the force of static friction is going to be the coefficient times, not the normal force. There is no normal force acting on the block. It's the contact force between the block and the book. And that's going to equal the mass of the block times A. So now, going back to our free body diagram, the contact force here is going to have to be equal to mvg because the block is not accelerating vertically. So filling that in, we have mu sub s times mvg is equal to mba. Hey, lovely. Mass of the block cancels out. And we have the coefficient of static friction is simply the ratio of A to G. Remember, we're solving for that coefficient, so we need to know the acceleration that we're going to have here. So the acceleration that we're going to have to go back and look at the system as a whole. The sum of the forces on the system are equal to the total mass of the system times the acceleration. The only horizontal force acting on the system that we care about is F. The reason why? The two static friction forces that are acting between the blocks, those cancel. So those don't affect the acceleration of the system. So this is really easy. It's just F acting on the system is equal to the total mass of the system, block plus textbook, times a. So the acceleration is simply F divided by mv plus ma. That's equal to the acceleration. All right? Oh, we weren't solving for the coefficient. We're solving for the force, right? So we've got an acceleration down here in our mu equation, and we've got an acceleration here. We're solving for F. So let's go back to this equation. Let's write that on the next page, as well as our mu equation. So we have mu sub s is equal to a over g, and we have F is equal to the total mass, mass of the block plus mass of the text times a. So solving for the total force here, let's see, we've got mu times g is equal to a. So plugging that in over here for a, we see that the maximum force is the total mass of the system times mu g. That's the maximum force we can apply where the block doesn't slide on the textbook. All right? We can also solve for all sorts of stuff. If we know what F is, we can see what the minimum coefficient of static friction would need to be, plugging this equation over here back into that one. So you could solve for whatever you would like based on these general equations. Again, the key here is the force of static friction acts to the right on the block to keep it from sliding. That's what accelerates the block. The force of static friction acts to the left on the textbook. Oh, I better complete the free body diagram. There is F acting on the textbook to the right as well. The reason the textbook accelerates to the right, F is bigger than F sub s. So it accelerates to the right. All right? So if the block doesn't slide on the book, then the acceleration of the block in this equation is the same as the acceleration of the textbook in this equation. That's a key understanding. If the block does slide on the book, then our static friction becomes kinetic friction, and the two accelerations in our equations for the block and for the textbook will not be the same. And we'll have to deal with that. All right? There it is. See you next time.